Hi, I'm Sebastian, and I'm going to talk about LLVM X-ray and how it can be used in HPC performance tool and generally in third-party profiling tools. So this talk is about, one second. Okay, this doesn't work now. This talk is about X-ray. So I'll give a little bit of an introduction to X-ray, then talk about how it can be used by performance tools in HPC in particular, and then talk a little bit about ongoing and future work for better integration. So what is X-ray? So it's kind of an integrated tracer in LLVM Clang that's been built to allow a sort of hybrid instrumentation that inserts static instrumentation points that can be patched runtime to enable tracing selectively. And there's like different components. There's the instrumentation approach itself. There's a runtime library with built-in tracers, and then tools to kind of convert and analyze the collected data. And this was originally developed by Google for performance debugging in kind of like production applications. For kind of more information, I'm referring to this talk by Dean Barris that gives a better overview about the whole system. Here I want to focus on the instrumentation approach and how it can be used by third-party tools. So I said I was going to talk about, all right, first, let's have a little bit of a look into X-ray instrumentation itself. And it's a kind of interesting hybrid static dynamic approach where we have these knob slats, which are like sequences of no-op operations that are inserted at compile time. And then at runtime, they can be patched by replacing them with calls to a profiling handler. So here is a little example on an excerpt of the main function. So this is the entry function. We have some like one of these knob slats here, and when patching at runtime, the X-ray runtime will insert a call to a trampoline function, passing a unique function identifier, and then this will be invoking the runtime library. So what does this system give us? There's near zero overhead because these knobs, if not active, basically don't impact performance at all. Also, compared to a fully dynamic instrumentation, like binary instrumentation, there is no reordering of the binary or JIT compilation necessary. So yeah, it's like a little bit more, not as invasive. And also patching is thread safe and very fast. So you can do it at any point in the program without breaking anything. Right, so I said I was going to talk a little bit about HPC performance tools. I want to kind of take a step back and look at how established tools handle instrumentation in different cases. And for that, I've selected a couple of representative tools. Scorpio and Tau are kind of like two very widely used performance tools in HPC. And TALP for profiling and tracing. And TALP is another tool that's quite useful for collecting high-level performance metrics. And since this is HPC, all of these tools have support for different parallel programming models like MPI, OpenMP, and more. Right, so let's look at how like different paradigms are supported. When you look at MPI, there's this PMPI interface, it's quite clear. For OpenMP, there's the OpenMP tools interface. So there's like a semi-standardized way how you do instrumentation for different models. However, if you go to general purpose regional instrumentation, then it's a little bit more difficult. And what a lot of tools historically and kind of still rely on is this f-instrument function flag, which inserts profiling probes at entry and exit points in each function. And this has kind of been adopted by a lot of tools because it's available by most compilers. But it also has a lot of drawbacks. Mostly there's like very limited control over what gets instrumented. It kind of instruments everything. So there's usually high overhead involved, and even dynamic filtering is tricky because even if you filter stuff out at the event handling level, there's still the overhead of calling the handler itself. Right, so different tools have kind of come up with solutions for that. For Scope P, there's custom compiler plugins for GCC and LLVM. And that's kind of one way to mitigate that. So they use, for example, fast dynamic filtering at the call side, which drastically reduces the overhead. And also some tools to use like fully binary dynamic instrumentation. However, there's, like with the compiler plugins, there's maintenance and development cost involved. And the dynamic instrumentation is kind of a little bit overkill maybe for just these like very simple probes, and can be error prone as well. Right, then just as a remark, there's also usually some kind of manual instrumentation API available. In this case, all of these tools use that. Right, so maybe you can see where this is going. I think we, as in the compiler, can do better, like provide a better infrastructure to tools. And kind of the question is, like LLVM already has X-Ray available for the internal tools, and it can be used as a third-party tool. So can we kind of use X-Ray as a more general replacement for like this classic F-instrument functions option? And kind of to reiterate the advantages, we have like fast dynamic adjustments. We have low overhead when we don't patch something. Also, maybe most importantly, we get all of these benefits without like a huge integration effort. So it's quite easy to use the interface. So kind of in essence, the idea is X-Ray could give us F-instrument functions on steroids almost. Right, so if X-Ray is so great, why are almost no tools using it currently? And in my opinion, there's two main aspects. First is that all of these tools, or a lot of the tools, have been developed when all of this wasn't available. So they kind of relied on like the basic interface or built their own thing. And secondly, X-Ray as a like third-party tool kind of has some drawbacks and limitations that need to be addressed before it can be adopted by a lot of tools. Right. I personally think that X-Ray has a lot of potential. So I'm kind of working towards changing that, and that's on like two different aspects. The first one is enhancing the core capabilities. A thing we recently did was enable shared library instrumentation for X-Ray, which was previously not possible. And then also looking forward, we want to add some more control over what is instrumented on the static level. Also, kind of to get people to use it, you have to like show them that it's, how it can be integrated and that it's beneficial. So we've kind of been working on integrating X-Ray into established tools. So recently, we've built a Scope P instrumentation backend based on X-Ray. And also we used X-Ray with our research tool for selective instrumentation. So I want to give some more detail into the shared library instrumentation and also the Scope P integration for X-Ray. Right. So as I said, we recently upstreamed this shared library instrumentation support, and that's already available in LLVM 20. You just pass this X-Ray shared flag, and it should work right out of the box. One caveat is that the built-in X-Ray tracing modes don't currently fully support it. They will run, they will record the functions, but the resolving of the identifiers doesn't fully work. But there's an OpenRC and a prototype implementation, so hopefully that can be fixed soon. Right, then a little bit of technical detail on this. So first, looking at how it works without shared libraries. So we have this embedded SLED data, which kind of contains a list of available patchable functions with their unique function ID. And when patching, this ID is baked in the trampoline call that then is passed to the event handler. Then going to like the full instrumentation with shared libraries. This is kind of how it looks. The difference here is here that in addition to this like main runtime we have for X-ray in the executable, we also have like a little runtime component in the shared library, and this on load will register with the main runtime, kind of inform it about the available sleds, the addresses of the trampolines, and yeah, just so that the runtime knows that these functions are available for patching. Right, and then based on load order, each object kind of gets a dynamic ID. And we use this ID to build what we call a packed ID, where we have this, this dynamic object ID and the static function ID to uniquely identify each function over the whole application. Right, patching kind of works the same as before. Only difference is that the main runtime kind of iterates over all the objects and then patches those that are available. Right, then, this is currently available for x86 and ARM. So I've put the link to the pull request here for the ARM extension for reference for anybody who wants to extend this to other architectures. Right. Okay, then the second thing I wanted to mention is the X-ray backend for SCORP. This is available on GitHub. Kind of easy to use, you just pass a flag and it will be used automatically. Here, we haven't added the shared library instrumentation yet, the support for that, but that's work in progress as well. Oops. So the question we kind of wanted to answer with this evaluation on SCORP is kind of how does this X-ray backend compare to a polished tool-specific static solution? And for this, we looked into how it compares to the SCORP, Clang, and GCC plugins. These are kind of polished solutions, I would say. Like they have this internal tool-specific efficient MPI, they embed the region information right into the binary, they do fast dynamic filtering at the call side, so you don't jump into filter functions. Right, so we looked at a couple of benchmarks from SPECT and also Ludash, and because they're kind of similar, I'm going to focus on one of them. Right, so important here is the red bar and the blue bar. Red is the X-ray backend, blue is the LLVM plugin, and kind of the dotted line down there is the baseline for Clang and GCC. GCC is also included here, the plugin, but it's not really comparable, so just see for reference. So let's first look at the full unfiltered configuration. And here you can see that X-ray actually has a little bit more overhead. However, if you look at the total overhead, then this is 7 times slower than baseline, so it's not usable for profiling or anything at all. And actually, we only observed this increased overhead in configurations that had too much overhead to be usable anyway. So then going to a dynamically filtered configuration, X-ray kind of at least matches or outperforms the static plugin. And that's quite interesting, once you go to a fully filtered configuration, basically meaning no tracing or profiling at all, then there's no measurable overhead for X-Ray here, compared to up to 6% with the static plugin, which 6% isn't a lot, but kind of this 0% overhead allows you to use the same binary for both profiling and for production runs. So it kind of makes the workflow a lot easier. Right. Then one thing I want to briefly touch on is increasing instrumentation flexibility. So this is like a direction for future work. So my goal is kind of to have X-Ray as a general purpose backend for third-party tools. And for that, there are some things that can be made more flexible. And that is that currently it's only inserting these points post-inlining and at functional level only. So a possible extension of that would be to allow like general region instrumentation, either via flags, for example. Like X-ray instrument loops or something like that to allow loop instrumentation, but also to kind of have a better system that allows you to put points, like measurement points and the IR, for example, via intrinsics, and then have them be turned into like regions you can measure for tools that want to have full control. Right, then I think my time's up, so I'm gonna skip over the summary. Just like a final thing, if anybody here is using X-Ray, either with the built-in tools or with a custom tool as a instrumentation backend, or wants to use it, then please come talk to me. I would love to hear about it. And yeah, thank you.